In this video, I'll be looking at the number of individual particles contained in a specific number of moles of a substance and how to do the calculations pertaining to that. Alright, so if we have exactly 1 mole of a substance, we know that it will have a standard number of 6,02 times 10 to the power 23 units in that substance. And we usually work with molecules, ions, atoms, or electrons. So that'll be 1 mole of any of those. But more than likely you'll not work with exactly 1 mole of a substance. You'll work with multiples or fractions of a mole of a substance. For example, if we have 0,2, a fraction of moles, a fraction of 1 mole of sodium atoms, how many individual sodium atoms do we have in that number of moles? Alright, so let's look at what we've got and what is being asked. We have the number of moles, lowercase n. We have the identity of the substance. So if needed for a calculation, we can calculate the molar mass from the periodic table. What is being asked is the number of atoms, so the number of individual particles represented by capital N. Right, so we'll use this equation. Na is your standard number of units in 1 mole, so it's Avogadro's number. Right, so the calculation will look like this. We're not going to use the molar mass, although we can use it to calculate the mass of sodium present. That's not being asked. So even though we can use it, it's not asked in this question. So we've got 0,2 moles, not exactly 1 mole. Okay, calculate that. Right, so the number of particles present is 1,204 times 10 to the power 23. And the particles is that is asked is atoms. Atoms of what? Atoms of sodium present. You can round that off to 2 decimal places, which will be 1,2 times 10 to the power 23 for your final answer. Okay. A more difficult example. So we have the same number of moles of oxygen. We know oxygen is a gas. How many individual oxygen atoms are present? Okay, so first of all, we know that Oxygen is one of the diatomic elements. So in its elemental form, in its pure form, it will always be two oxygen atoms bound together in a molecule. So oxygen's formula will be O2. And that means that for every one oxygen molecule, two atoms of oxygen will be bound together. So for every one molecule, there will be two atoms. That also means that for every 1 mole of oxygen, there will be 2 mole of oxygen atoms. 1 dozen oxygen molecules will be 2 dozen oxygen atoms. Right, so again, we've got the number of moles, we have the identity of the substance. What is being asked is an individual number of oxygen atoms. So we'll use this equation again. Zero comma 2, the number of moles, times Avogadro's number. That gives us again 1,2 times 10 to the power 23. What did we calculate? We haven't calculated oxygen atoms yet. We've calculated the oxygen molecules, because the number of moles of oxygen molecules is given. So that will be oxygen molecules. What is being asked is the oxygen atoms. So if that's the number of molecules, there will be twice as many atoms, because one oxygen molecule consists of 2 atoms. So 1,2 times 10 to the power 23 oxygen molecules will have to be multiplied by 2 to get the number of individual atoms. So that means that the number of oxygen atoms is equal to 2 times the number of oxygen molecules. Which is 2,41 times 10 to the power 23 oxygen atoms. The same idea will present if you have, for example, ammonia. For every 1 ammonia, 1, 2, 3 hydrogen atoms. So if you calculate that there's 1 mole of ammonia, it means that there's 3 moles of hydrogen atoms present. If you have 2 moles of ammonia, it means that there will be 6 moles of hydrogen atoms present. So however many moles you have of a substance, be very careful to read your question carefully. Are they asking for the number of molecules or for the number of formula units of ions, or are they asking for the number of individual atoms? Then you will have to add 1 step to get to the number of individual atoms.